Hi guys, so this video has a very important topic. It's waves and sound waves included as well. Okay, so this is a topic that would most likely come for your exam on Monday, right? So it's important to kind of pay attention to everything, the definitions, the formulae, the difference between the transverse and longitudinal waves, and we'll discuss all of that in this video. Okay, so the first thing we need to do is distinguish between transverse and longitudinal waves. So essentially, in a longitudinal wave, the medium or particles move in the same direction as the wave, whereas in a transverse wave, the medium or the particles move perpendicular up and down to the direction of the wave. And we'll see some examples of these as the video goes on. So they want us to state one example of each of the waves. So a transverse wave could be electromagnetic waves. That's an example, right? Longitudinal waves could be sound waves. That's a very easy example for both of them there. And here we have the most important equation in waves. It's called a wave equation, which states that the velocity of the wave is equal to the frequency multiplied by the wavelength. Okay, and it's written like this: V is equal to F lambda. Right, so here we could actually practice one. A wave motion has a frequency of 10 hertz, which is the frequency, and a wavelength of 250 meters. Calculate the speed of the wave. So I write my formula: V is equal to F lambda, and I put in the information 10 multiplied by 250, and this one is very easy. It's 2500 meters per second, right? It's velocity, so that's the units there. Okay, so here's an example of a transverse wave. You see, it goes up and down, and you can imagine that this is a particle here in the wave. It will be moving up, and then it will be moving down. So that's what we mean by the direction, and the movement is perpendicular to the direction of the wave, right? The wave is going in this general direction here. Okay, so some important definitions we need to know about a wave like this is that the height of the wave, the maximum height here, this is the amplitude of the wave, right? So the amplitude of this wave is 0.5 millimeters. You can read it off right here, right? Another one is the period or the wavelength, right? So the wavelength is measured by connecting any two heights, right? So you'll see we'll get into the definitions very soon, right? Or you could take the last two at the bottom part most of the wave, right? So from here to here is actually 1 to 5, so that's 4 milliseconds, right? So that's the period or the wavelength of this wave, right? So this is what they were actually asking you here. So they wanted the amplitude in meters, right? So we have our amplitude in millimeters, so we needed to convert that to meters, right? So this would be your answer here, 0.0005 meters. They want the period in seconds, right? So our period was 4 milliseconds that we just calculated there. So to convert milliseconds to seconds, we divide by 1,000 and we get 0.004 seconds. And frequency, this is the second thing you need to know. Frequency is essentially 1 over the period, right? So if the period was 0.004, your frequency is 1 over 0.004, and you'll get 250 hertz. That's the frequency there. The next thing is to state one property of an electromagnetic wave, and I just stated a few here. Electromagnetic waves have the same properties as any other wave, which means it could be reflected, it could be refracted, it could transfer energy from one piece to another. So a lot of different properties that you could come up with there, right? Okay. State the factor on which each of the following characteristics of sound depend on. So the pitch of sound is actually dependent on the frequency, right? So if you have a sound wave going like this, if you have a wave going like that, right? Well, that's not a sound wave, right? That's just a regular wave, but it's easier for me to show you here. Rather than a wave going like this one would be a higher pitch, right? Because the frequency is more, right? And the loudness depends on the amplitude. So if you have a great amplitude or a small amplitude, this would be a quieter sound than the bigger amplitude, right? So very easy things to remember there. Okay. A sound wave completes 3 cycles in 6 milliseconds. Calculate its frequency. So by cycle, they mean the trough to trough, right? So they complete 3 of that in 6 milliseconds, but we want to know how much is 1, right? So 1 cycle would simply be 6 divided by 3, which is 2 milliseconds. And you know we need to convert the milliseconds to seconds. So 2 milliseconds is actually 0.002 seconds. And then to find the frequency, we simply take that 1 over 0.002, 1 over the period, right? So essentially this is 3 periods, yes, 3t is equal to 6. So to find 1t, we just divide it by 3. And to find the f, we put 1 over t, and we'll get 200 hertz. A very simple calculation. Easy marks there. Okay. So again, they want us to state some more properties of electromagnetic waves. We know that already. Part 2, visible light is a type of electromagnetic wave. State 2 other types of electromagnetic waves, indicating whether the wavelength of each is higher or lower than that of visible light. So this is something you need to remember, need to learn, is the electromagnetic spectrum, which has a whole lot of different examples of electromagnetic waves and their wavelengths, right? So there are a whole lot that you could choose from. To either choose 2 random ones, gamma waves, which have a higher wavelength, and radio waves, which has a lower wavelength than visible light, right? So the spectrum, visible light is in the middle here. So going that way, you have the radio waves. Going this way, you have more of the gamma and the X-rays, right? So you should Google up that or check it in a textbook and learn that, right? It's very important, and you get some easy marks there. Okay, here are some calculations here. Electromagnetic waves of one wavelength are absorbed by a solar panel, and waves of a longer wavelength are emitted. If electromagnetic waves of wavelength of that 2 by 10 to the minus 7 meters are absorbed by a solar panel, and waves of wavelength this are emitted, calculate the frequency in each case, and then the decrease in frequency. Okay, so we have all the information here, and we have our formula, V is equal to F lambda. So they want us to calculate the frequency. So therefore, we need to make frequency the subject of the formula. Is very simple. We just need to move this lambda over to the other side. So frequency would be V over lambda. Okay. So we already have our V. All electromagnetic waves have the speed of light, which is 3 by 10 to the 8. We need to remember that, right? But they did give us it here. All right. So this is going to be 3 by 10 to the 8 over, and the first one is 2 by 10 to the minus 7. Okay, so you need to put that into your calculator, and we'll check out the frequency here. It's going to be quite a large number. So I'll get 1.5 by 10 to the 15 hertz. All right, that's the frequency for lambda 1, right? So similarly, we just replace the wavelength over here with the one for lambda 2. So it'll be 6.5 by 10 to the minus 5 this time. And for lambda 2, I'm getting 4.6 by 10 to the 12. Okay, so these are my 2 frequencies. And now they want me to just calculate the decrease in frequency, which is simple. I just need to subtract the 2, right? Okay. I'm subtracting that from 4.6. and I'm going to get 1.495 by 10 to the 15. Okay, so the next part is we assume that the useful energy transferred to the solar panel is a constant K times the decrease in frequency of the waves, right? So the decrease in frequency would kind of determine the energy that they put out, right? So they give you the formula here. E is equal to K multiplied by the change in frequency. Cool. Now they want us to calculate the energy. Very simple. So E is equal to K multiplied by the change in frequency, which is 1.495 by 10 to the 15. Very simple, right? So this is the amount of energy here. It's actually, you just need to write out the formula, right? So it will be K multiplied by 1.495 by 10 to the 15 joules. Right? Because it's saying in terms of K, they didn't actually give us what K was. Okay, part 3. With a change of conditions, the wavelength of the wave now absorbed by the panel increased to 6 by 10 to the minus 7, but the emitted wavelength remains the same at 6.5 by 10 to the 5. Right? What fraction of E1, the original energy transferred, is now transferred to the solar panel? So again, very simple. We need to calculate the change in frequency again, so we could calculate the next E that is created, right? So we don't need to do the one for number 2. Number 2 is going to be the same because it's emitted the same way. So the new absorbed, I have more space now, right? So you have new absorbed wavelength. So F is equal to V over lambda, which is 3 by 10 to the 8 over 6 by 10 to the minus 7. So let's calculate what that would be. So this is 5 by 10 to the 14. Great. So now we need to calculate the difference again, right? So it's going to be 5 by 10 to the 14 minus the 4.6 by 10 to the 12 as before. And I'm going to get 4.95 by 10 to the 14, right? So this is the new difference in wavelength. So now I put this back into the energy formula, which is K multiplied by 4.95 by 10 to the 14, right? So now they want to know the fraction of E1, right? So they kind of want to know the ratio, right? So the fraction is going to be E2 over E1. I'm labeling this E2, right? This is in E1. So it's going to be K 4.95 by 10 to the 14 over the K by 1.495 by 10 to the 15. So we could cancel the K's and the K's, but now we need to put those two over each other, right? So 4.95 by 10 to the 14, that's divided by 1.495. Okay, so your fraction would be exactly 1/3. Okay, so this is your fraction here. All right, so again, this was a more complicated question, but using the same easy formulas as we are learning already, right? So if you didn't understand it, you could always go back through the video again and take it slow, read the question carefully, and you will get it out, right? Okay, so here's an example of a slinky making a wave, right? So they're generating a wave essentially, right? So indicate on figure 2F, which is this one here, labeling a crest and a trough, right? So these are more definitions with the topmost part and the bottommost part of the wave, right? So the topmost part is called the crest, the bottommost part is called the trough. Very easy. And the second part is draw label arrows on figure 2E, which is this one, the direction of the wave and the direction of hand movement needed to produce this wave. So this is a transverse wave, right? So the direction is always going towards the right, right? But the hand movement, which is, remember the first definition that we learned today, was with a transverse wave, the movement moves perpendicularly. Well, you could kind of imagine like if you was whipping a hose, or the same way like the slinky. To generate this wave, you have to move your hand up and down, so perpendicular to the direction. Okay, and finally in part 3, indicate on figure 2a the direction of hand movement needed to produce a longitudinal wave. Okay, 1 second. Okay, right. So on figure 2a, remember in a longitudinal wave, the hand movement is in the same direction, or parallel, right? So you could see that I drew my arrow there in the same direction as the direction of the wave. Very simple. Okay, in a classroom demonstration, a student uses a slinky spring to generate waves of frequency 5 Hz with 0.65 meters separation between successive crests. What this means, this is the definition of the period of the wave, right? Determine the speed of these waves. So you know your formula, V is equal to frequency multiplied by wavelength, right? So we have the frequency and we have the wavelength, right? So determine the speed, very simple. It's going to be 5 multiplied by 0.65. So we could put this in our calculator. Let's see what we'll get. And I am getting 3.25 meters per second. Okay, very easy calculation there. Deduce whether the velocity of a sound wave will increase, decrease, or remain constant when the wave travels from a denser to a less dense medium, given that the frequency remains constant but the wavelength decreases. Well, this is very simple because we have our formula here, V is equal to F lambda. So you could see that the velocity of the speed of the wave is directly proportional to the frequency and the wavelength. So if by chance the frequency were to increase, the velocity would increase. If the frequency was going to decrease, the velocity would decrease. Similarly, for the wavelength, if the wavelength increases, the velocity increases. If the wavelength decreases, the velocity decreases. We call this directly proportional. So, if the wavelength decreases, the velocity will also decrease because they are directly proportional. The next part, compare the waves produced on the slinky spring in part B with the typical sound wave in terms of the motion of the particle. So this is the same thing as asking the definition or the difference between a transverse and a longitudinal wave, right? So the wave on the slinky spring was transverse, which means that it had to go perpendicular to the direction. And in a sound wave, the particles go parallel to direction. And this is all the important notes that you would need to know to answer your questions on waves.